All right, this is the last of my videos that are dealing with x going to infinity. First thing I wanted to do was fix that -1 from the last video, so that's done. All right, more examples. I want to sort of remind you of some things too while I'm doing these. Let's compute the limit as x goes to infinity of tangent of x. So as usual, the first thing I'll do is grab a calculator and graph it and see what it tells me. Yeah, clear your y1 and your y2. Go up. Tan is its own button. Just put an x in the parentheses and finish it off. And I'll do zoom 6. Oh, what? I forgot. Let me check radian. Make sure whenever you're dealing with trig, you've got radian covered. Now I'll do zoom 6. And you ought to know. You've seen this graph probably, I can't tell you how many times in your life. At every odd multiple of pi over 2, there's an asymptote. But at the same time, I do not see any indication from the graph that it's honing in on a particular y value. In fact, when I go to the table, look at the numbers that are popping up. I got a 10.24, -4.6, -1.7. It jumps around, and that's because even for really big values of x, it's the same looking graph as it was just from the basic view. So what that means is that the limit is not going to exist. It's because of the alternating, or what would you call the periodic nature of tangent. It has a period of pi. That means it does the same thing every pi. Let's try another limit. This time I think I'll do tan inverse of x. I want you to make note of something. As terrible as the notation is, when you write tan to the -1, it always means arctan or inverse tan. It does not equal 1 over tan. That we do not use that notation. It's an unfortunate notation, but it is something we just have to live with. So I'll write this here in the hopes that it fixes a lot of errors that people might have throughout the course. So anyways, arctan is what I want. If you look above, let's see here, if you look above the tangent button, you have tan to the -1. There it is, arctangent of x. I'll do zoom 6. And you get a graph that goes through the origin. I think I want to zoom in a little bit on that one. That seems kind of small to me. I don't care about x max and x min, but the y max and y min I think I'm going to change from -2 to 2. Now let me take a look at this graph. So very nice looking graph now. I can see its features fairly well. Let me go to the table, and I still have huge values in for x, so let me see what the values are showing me. And if you look at these values, I'm getting 1.5707, 1.57079. So you can see here, through large values of x, it is honing in on the number 1.571. I'll do 3 decimal places. Now you may remember that inverse tan is an odd function. That means whatever it does in the first quadrant, its mirror image is in the third quadrant. So let me go back to my table set. Now I want to deal with the negative values. So I want x to be going to -infinity. And that means I will put a negative in front of my huge table start values. And I will change my table increment to also be negative. And let's take a look at the table values. Now, with huge negative values, the table values are all the y values are about negative 1.571, which, as I mentioned, tan inverse is an odd function, so this shouldn't have been a surprise. I want to do an even better looking graph than the calculator has because I want you to see it. When you type in the function in my graph program, you have to type in arctangent of x, and you don't, what's this? Okay, my bad. You type in a tan of x. So get rid of the arc, or RC part. Okay, there's our graph. Let me change the horizontal asymptotes to negative 1.571 and positive 1.571. I touched something. Come back here, graph. Okay. Now, you can see that the graph is totally between those two horizontal asymptotes. It actually should be no surprise. The horizontal asymptotes are actually occurring at negative pi over 2 and positive pi over 2. But that's not required. I was happy with a decimal for an answer for these types of problems. So the top horizontal asymptote is y equals 1.571, and the bottom horizontal asymptote is negative 1.571. So that graph, the graph program does shows these things a lot better than your calculator does. Your calculator's limited in its graphical representation. All right, moving on. I just thought I would throw out a bunch of different things at you and sort of try to remind you of a few things at the same time. How about the limit as x goes to infinity of e to the x? And while I'm at it, how about x goes to negative infinity of e to the x? So I'll do like I did before and get a graph of e to the x. If you want to find e to the x, you have to go on top of the ln button and do second e, and then you put an x up in the exponent, and you got to delete whatever else was in there. As usual, zoom 6. Now you can see a graph that's steadily increasing throughout throughout this screen. In fact, it's pretty clear to me this graph just shoots up very quickly, and this probably bears worth keeping in mind that the exponential functions are going to grow faster than any other type of function we deal with for the most part. There are a few novelty things that come out here and there, but typically of the types of functions we deal with, nothing grows faster than the exponential functions. As x goes to infinity, you can see that graph just shoots right up. You've probably seen this graph before. There's nothing special that's going to happen. It's not going to turn and suddenly go downward or something like that. It's pretty simple. The limit as x goes to infinity of e to the x is infinity. If you need more details, just look at the table values. Let me see here. Now, I have huge numbers in. Oh wait, those were negative numbers. I think I need to change my table. I need to get rid of the negative out of there. I'll just start it at 9999 and increment it 10,000. Second graph. Now over there are errors. That doesn't do a lot for me. In reality, what these errors are is that they are overflow errors, but I don't know that by just looking at this screen. All I know is it's an error. Oh, that negative one was in there. That was unintentional. But these errors do nothing for me. So I have to figure out some other way to convince myself that it's going to infinity. I mean, the graph, we only saw a small portion of the graph. it wasn't, I mean, if you've never seen it before, you may not have a clue that it continues to go upward forever and ever and ever. Let's use smaller numbers because maybe the calculator just can't handle the size of these numbers. So I'll start at 999 and I'm still getting errors. All right. So, and 999, x equals 999 is nowhere near what I consider a large number. What I'm going to do instead is evaluate this directly. Let me do e to the, and I'll pick some different numbers and see what's happening. I'll put e to the 99, and it gives me this huge number, 9.88 times 10 to the 42. All right, let's try another one. Let's try e to the 9, oh wait, let's try 500. Okay. Now this I can count on. Overflow. The error is actually overflow. That means it's so big, it's too big for the calculator to compute. So I feel comfortable now that this limit is infinity. All right, now let's move on to the limit as x goes to negative infinity of e to the x. From the graph, you can see it kind of dies down to the left. Let's get out of that thing. I'm going to put in huge negative numbers for the table. Negative 999, I'll start the table at, and I'll increment it by negative 1000. So let's go and look at our table values again. Well, it says 0. As far as I go, I can't. No, the problem with scrolling is I got to scroll through the x values. Of course, I jumped into the positive numbers that were left over from before. I mean, to me, the graph is pretty obvious that as you go to the left, or as x goes to the left, the function itself is hugging the x-axis, which indicates that the limit is 0. But I'll do some examples. E to the negative 99, I get 1 times 10 to the negative 43. That's a super tiny number. Let's try e to the negative 200. Syntax error. I believe, oh, I put a I hate that. I put a minus instead of the little negative sign that they use. Look at that, 1.38 times 10 to the negative 87. To me, that's enough evidence to conclude that the limit's going to be 0. Well, last time, we did a function that's inverse, and I'm going to do the same thing here. Oh, make note that y equals 0 is a horizontal asymptote of this graph. So as arctan is the inverse of tangent, the natural log function is the inverse of e to the x. So let's try to figure out the limit as x goes to infinity of ln of x. As usual, I'll put it in y1. We have a button for ln. There it is. Put in the x, parenthesis, and as usual, zoom 6 to me is like home base or something. All right, so you see a graph that's increasing. It's going up, but not so fast. It's very slowly creeping up, if I had to say. If I trace some values, let's see where these x values are, what x and y values are. As I scroll and use higher and higher x values, the y values are tiny. So let me go into the table. I need to put in big positive numbers. So let's do like I did before. I'll put 9999 and I'll increment by 10,000. Okay, let's take a look at our table values now. Okay, so for 9,999, my y value is 9.2. I'll scroll down here. 11, 12. These numbers are not huge at all. I mean, the x values are giant. What do we got? 369,000, and the x value, and the y value wasn't even 100 yet. This one I kind of have to tell you because it is actually infinity. This limit is actually infinity. So the way you can do it is through logic. You can convince yourself. Suppose you think that there's a horizontal line, y equal b, that is completely above the graph of y equals ln of x. Somehow the graph is below some imaginary y equals b line. Let me grab a picture of this graph and I'll sort of indicate what I mean by this. Let's copy the graph. Gotcha. Let's make it a little bigger. See, the thing about a graph like this, it almost looks like it levels out. Like it almost looks like there might even be a horizontal asymptote or something somewhere, but that's not actually the case. Whoa, I went a little crazy on that stretch. Let's bring you back. So let's say this line y equal b is completely above the graph, or you think you can come up with some line that's completely above the graph. Well, if I take as an x value, if I plug in x equals e to the b plus 1, the natural log of e to the b plus 1 is b plus 1, which is bigger than the imaginary line drawn for b. So in fact, this function does go to infinity, just not very fast. It's a very slow growing function.